Hello guys, very happy morning to all of you, and now we are just going to see the welding, because in the previous chapter I just explained you a little bit of extra things about the welding and how each and everything is been occurring. So without wasting time, let us get started. So the thing is ultrasonic welding, so which is perfect. So ultrasonic welding, I think so we don't know, because ultrasonic wave, high frequency wave is used. The small it means a bit of particles will be using that we will just strike so much times and the welding will occur. Okay, surface are held together under light normal pressure. Temperature is one of the melting point, and this is also a process of solid state welding. Okay, so but precision welding is not a solid state welding, but we do tell it as a little bit of solid state welding. So metal and non-metal can be ultrasonic welding is same as ultrasonic machining. Only lap joints we can just do and the butt joints we can't do. Okay, so weld thin material sheets and fields and wires on the attaching thin sheets through the heavy section. Just normal things, raw doesn't need a complicated thing to learn this. So you can see maximum thickness. You can see maximum thickness is 2.5 mm for aluminum. Okay, so if I just show it on video means it will be a better thing. So you can see this one. 35 kilohertz 120 watts ultrasonic welding. You can see it's a thin sheet and they are just see. This way you are able to see. So little heat like will be there, and as well as the striking capacity will be so much higher. See, that's it. Finished. You see the sound coming. I think that sound is an ultrasound. No, we just took it outside. This way you are able to understand. So maximum thickness 2.5 mm for aluminum. So you can see in this ultrasonic number of metals, dissimilar metal combination of non-metals can be joined, such as aluminum, ceramic and all glasses. So temperature, you can see temperature, heat we do not give, it means temperature we do not give, itself heat is produced. Because of continuous striking motion, itself the heat is produced. So okay, equipment is simple and reliable, low surface penetration, less energy needed. Joining dips and okay, microcircuit separately, ultrasonic is mostly for microcircuits and electrical contacts and welding infinity and reactive and ultra thin materials. So next one is explosion link. So only pressure place here in explosion link there is no temperature needed. Okay, you can see there will be, it means I'll just show you. So explosion link is most explosion. See, export mode. So I think so I can see this one.
Have you ever heard of explosive welding? As the name suggests, this welding method uses the immense force of an explosion to bond materials together. The process is surprisingly straightforward. First, the metal components to be welded are arranged on top of each other, separated by a small gap. An explosive layer is then applied to the surface of the top metal sheet. Upon detonation, the explosion propels the upper sheet at an extremely high velocity, causing it to collide forcefully with the lower sheet. This intense impact completes the welding process in mere microseconds, creating a durable metallurgical bond. Have you
ever heard of the explosive?
Okay, that's the thing. So one plate is placed on over the other plate using a small, you can see welded, it means clear that what? Where is that one? Where is that one? Where is that one? So see, this kind of puddles as well as the tack weld, little bit of small thing will be, you can see that we will just place here, and you can see now the critical blaze plate and the explosive will be placed over the welding plate. So suddenly the explosive ball will ignite, and within 1 second everything will burn, and enormous gravity will lead to push the droplet to the bottom plate. So you can see immense pressure is so much, and then to air and water and vacuum. So surface conductor of the base plates will be blown off. So due to high pressure, especially well suited to metal that are poured to metal joints, and when heat wells. So it is aluminum on steel, and as well as titanium on steel, and aluminum to copper. So important for critical velocity and critical angle. So cladding plates must be supported. I think so cladding plate must be supported with the tack weld support at the edge and the metal sensor. Okay. So you can see the detonation velocity should not exceed 20% of the sonic velocity of the mode. Okay. Suppose if it just exists, means already the plate will have a lot of problematic things. The detonation velocity should not exceed 20% of the sonic velocity in the metal. Okay. High explosive or high vertical velocity, you can see TNT. It means see the speed more than, it means more, it travels more than sonic speed. And medium velocity, it means dynamite. Okay, we grind the first spoon for fish and metal oxide will be removed. Okay, by using the roll also we'll just make it adjustable. So can bond many dissimilar metals, normally unweldable metals, which are not easy to join and we can melt. So the lack of heating process makes treatment here the process is compact and portable and easy to contain. This kind of thing. Inexpensive, no need for surface penetrations. Many it means metal oxides are removed due to pressure itself. Very large plate can be cladded joints to means hot tube as well as to heat exchanger. So you can see here definitely ductile material only should be, because if you use brittle material definitely the crack may occur so much. So next one, cladding plate can't be too large, noise and blast sound very high and protection error. So mostly carried out in the sand and water and burn in the vacuum chamber. Okay. So next one is plasma arc. Okay.
In plasma arc welding, the construction of the torch is totally changed to increase the temperature of the arc. The tungsten electrode is placed inside a specially designed nozzle that focuses a stream of inert gas moving at high velocity into a constricted and narrow path. When an arc is struck, the inert gas is forced to flow through the region of the arc. This causes the gas to ionize due to the electric arc and form plasma. The arc and the plasma then flow through a narrow constricted opening. The sudden decrease in the flow area increases the velocity and the temperature of the plasma arc. They exit the nozzle at almost the speed of sound and also reach temperatures of more than. If we're trying to pierce stuff, like we should not be trying to pierce like
This is plasma cutting.
you can see how that just splashed everywhere, right? That's no good for a nozzle. If you're trying to pierce anything, you should always hold it at an angle and let it fly up and away in a different direction. If we're trying in plasma arc welding, it looks like a very fancy name for a welding process. Plasma arc welding is a type of arc welding procedure which uses plasma to weld metals and materials. The working of this welding type is very similar to that of TIG welding. Normally in TIG welding, a tungsten electrode is used to strike an arc between the welding apparatus and the workpiece. In plasma welding, the same thing is done, but in a different manner. We'll explain the whole concept by comparison. In a regular TIG welding torch, we have a tungsten electrode, the pathway for the shielding gas, and the handle for the user to hold it. Plasma arc welding, it looks like a very fancy. In a regular
See the plasma cutting, how much powerful it is. So the same thing, the plasma, it means the gas will be passed and tungsten will pass and the current will flow. So due to this the gas gets ionized, and you can see while current flows while the arc we pass the gas, then this gas ionized to plasma. This plasma heat then melts the welding. Okay, similar to gas tungsten arc welding, except the plasma caused by the arc constructed by the water cooled surface. That's it. Okay. So you can see uses ionized gas jet plasma to cut materials restricted to the oxygen welding. high velocity electrons can generated by the arc impacts gas molecules and ionizes them. Ionized gas force the nozzle and argon is used as shielding gas. So next one, advantage, plasma arc has a directional stability and lower heat input. Plasma directional stability and lower heat input and lower filler material. No edge group stress rate. Okay, expensive, flat, horizontal. Maximum 25. Large amount of UV and IR is emitted. So you can see stainless steel and applications, nickel based alloy. And nickel based alloy where we can use. You can see about the oxidizing flame. So unsuitable for refractive materials, coating like aluminum or graphite nozzle for rockets. Okay, monal. Carbon is oxidizing images too. So you can see the flames of are usual monal nickel carbon copper based alloy. So carbon, so oxidizing flame. Okay. So next one, diffusion. Diffusion welding is a solid state welding method which produces, it means different material we can just run. You can see while it's been the welding is like 50 to 80% of the, it means melting temperature of the parameter will occur. Okay, time weakness I think so. Produces high quality bond with good strength with lesser no distortion. Can join dissimilar metal also. Solid filler metals may or may not be inserted. Metals like some welding materials like aircraft rocket industry, it means boron, titanium, aluminum, ceramic, composite. So most of the materials. So for aluminum and for aircraft rocket industry, we had diffusion welding. Okay. So brazing and salting. So brazing and salting, brazing only blue flame circles, no white cone. So base metal no melt, no red hot condition. Only filler metal is melts. Okay, base metal only filler metal melts. 400 degrees Celsius above, more means brazing. 400 degrees Celsius less means soldering. So both filler metals needed. Yes, definitely. So brazing have little more strength and salting has no strength. And brazing is a joining of metal through which uses heat and filler metals while melting temperature above 450 degrees, but below the melting point of the metal being joined. Yes. Brace metal low belt. Yes. Only filler metal belts. Yes. So I'll just show it to you.
Bracing and soldering are similar processes to each other. Both involve the melting of a filler metal to join two or more components without melting the base material of the components. In this video, I'm brazing copper to copper using a 15% silver alloy filler metal. It melts above 1400 degrees Fahrenheit. Very basic process. It's a stronger joint than if I were to solder this particular joint together, and that's desirable for the build quality.
See, in this kind of white flame is there.
Okay, so for this smaller piece, I made sure that my flame is going down there, just like so.
So the same way we are seeing. So strength of brazing alloy is sustainable towards the base metal. Temperature of brazing is lower than base metal. Due to capillary action, capillary attraction, this draws easy anyway, so no excitation here. So you can see by using capillary action we are doing this. Capillary action is the best, and all metals can be joined, suitable for dissimilar metal, quick and economical and coercion mode. And here you can see iron tends to attract more electron from the carbon. Okay, copper. Okay, that's why the breaking of each and everything is occur. Okay, copper and iron. So copper becomes negative, becomes positive, and reaction occurs. So that's why we don't use like copper and iron thing. Brassing metal, you can see brazing brass, copper is 50%, zinc is 40%, manganese and bronze, nickel, silver, each and everything we can just do it. So extremely clean surface here due to capillary action. Flow used are a combination of the borax and boric acid and chloride, and the fluid is another unpopular combination is 75% borax and 25% boric acid. Okay, you can see strength, it means up to certain gap only the strength will be, and after that the strength will decrease. Okay, these are having So next one is soldering. So by definition, soldering is a basic type which is below 450 Celsius. So it's means strength of filament metal is low, and in bracing we need torch and filament. So no, it means solder part is higher, no flame is given. Soldering is used, soldering is used to need leak-proof joint and low resistant electric joint. Okay, that's it. So I think so use a copper wire, and if you can easily join it, due to high resistance, more heat occurs, that may be little problem. So to reduce resistance, we use a solder. Selection of color solder for job, selection of copper joint, okay. Application of the flux and solder, sufficient heat to allow the molten solder to fill the joint by the capillary action of the heat. Okay, the removal of flux and residue is necessary. So next one, gold is early brassing solder, and most solders are alloys of lead and tin, and three commonly used contains 60%, 50 and 40% tin, and this thing. So solder flux, so flux is hydrochloric acid sometimes, and zinc chloride for galvanizing iron. So silver solder is used for high temperature service of nature. Okay, next one, difficulty with gray cast iron. Soldering and bracing are difficult of gray cast iron due to surface contamination as graphite has low surface, so it's not easy to build that. Okay, guys, that's it. We have just completed the entire building. So now we will just go and see the problems. So take 2 minutes of it, and let us meet again. So you can see the ratio of acetylene and neutral flame is 1:1, and oxyacetylene is more than 2, so it means if okay, oxyacetylene gas will be okay. The tablets have enough one, so they have just not given enough neutral flame or any kind of other flame, so we can just go with the P. So if anything you know, take neutral flame. So if oxyacetylene means oxidizing flame they are given, we can just take 3008 oxidizing flame. Okay, carbonizing flame means it is less than 300,000. Okay, less than this one, not greater than 3000, and neutral is this one. Okay, oxidizing flame is used in gas welding in the joint medium carbon steel having high melting point. Medium carbon steel. Okay, in gas welding oxidizing flame produces maximum temperature. Guys, the oxidizing flame is maximum. Okay, medium carbon steel, mild steel. Okay, the temperature of carbonizing flame is neutral flame. Okay, the temperature of carbonizing is that of is lower than acceptability. By which one of the following gas diastine is being welded? It means C, gas, slightly oxidizing. So in oxidizing completely means the volume of the oxygen means for neutral well means yes, definitely 1:1. Okay. Wait, another interesting question will come back this. Okay. In gas welding of a mild steel using oxidizing flame, the total number of suppose if it is a neutral flame means if acetylene is 10 milliliters, definitely oxygen consumption will also be 10 liters. Okay. Okay. So this one I just explained. This one is okay. In DC welding power source, so open circuit voltage, 100 volt, short circuit current 1000. So maximum current is 100 divided by 2 into 1000 divided by 2. So it's about how much? 50. This one will just take. So voltage equal to 10 plus of 5. So let's say I have just given. No, so you just took like this. In manual welding, so what I just told, manual welding is CM, and automatic welding is BAO. Okay, voltage means robotics. In manual welding, the equipment should have the doping characteristic in order to maintain high constant arc length sensor. Okay. So max power you can definitely do it. And next one, so this one is a constant. It means voltage equal to A plus of B times of L. So open circuit voltage, current only there is given I equal to 160 ampere, not SCC. And steel of thickness, the welding voltage and current. Wait, SCC. SCC is equal to I divided by 2. Yes, so 160 divided by 2. So welding voltage and current, definitely you can see open circuit voltage is given, current, that's it. Because we need OCV and as well as SCC, that's it. I think so you're able to understand. So next one, arc welding space doubles. Welding speed doubles and all other parameters remains constant, and then the cross section area of the weld will increase. What happened? So in this metal deposition rate is important. Metal deposition rate means millimeter cube per second. Okay. So area into of velocity. Just one sec. It's okay. Now it's okay. So area into velocity. So for example, if now area is same, velocity okay. So now A1, this one V1 into A2 into of 2 times of V1 get cancelled. So the cross section area of the weld you can see A2 is A1 divided by 2. So what will happen? It will reduce by 50%. Okay, that's it. Okay, so if velocity double, the area reduced by 50%. If area double, the velocity is reduced by 50%. Okay, vice versa. Power is constant in this unit. So metal deposition rate, this one. So next one, straight line curve they have just given. So they are constant Oh, they have just asked the power. Okay, power, I think so you can easily do it. Okay, so they are asking the I. It means what is the current? So I equal to SCC divided by 2, V equal to OCV divided by 2. Okay, that's it. I equal to SCC divided by 2. Given SCC, put here, OCV put here, and we will get I as well as the voltage. So next one, so voltage of arc is given. Okay, it means next one, voltage high, current is lesser. So linear power is OCV and SCC. So I equal to OCV SCC divided by 2 and B equal to OCV divided by 2. So voltage of arc equal to 20 plus of 5 times of length. So length is 5 mm and this one V1 will become certain length. So 50 to 525 then 45 is voltage. Let us take like that. So next one V2 is 7, so 35, so 55 volt. Okay, then current equal to I equal to lesser current, high current, ampere, lesser voltage, high current, high voltage, lesser current, 400 ampere. So next thing, what is the relation between this one? So I divided by SCC plus V divided by OCV equal to 1. Okay, so put here I as 500 ampere divided by SCC plus a voltage 45 ampere, 45 volt, OCV equal to 1. Okay, now you can see, I think so you can see it's on. Okay, because now we had a two relationship, so you just equate this kind of two relationship. It's like this, and based on that OCV and SCC we can directly easily can calculate. Okay, that's it. So we can go for the next one. So this one it means 3 volt plus of I equal to 240 DC. Okay, they have just given the characteristic voltage and for maximum arc power at a voltage should be. So they are asking maximum power equal to how much? For maximum arc power, okay, they haven't given any kind of voltage and I. Okay, so power equal to V into I. I equal to 240 minus of 3V. It means voltage into 240 minus of 3V times of voltage. 240 of volt minus 3V square P. So maximum power is with respect to dP divided by dV equal to 240 minus of 6 times of V. So 240 into 6V. B equal to 40 volt. B is the answer. Okay. Okay, or you can also do by this also. You can see 3 times of V, 3V plus of I equal to 240. So put 3V divided by 240 plus I divided by 240. So V is 80. V divided by OCV plus I divided by SCC equal to 1. Suppose you can see OCV equal to, it means V equal to OCV divided by 2. OCV becomes 80 divided by 2 is voltage. So next one this. So you can see VA characteristic is given by IT square equal to 61 and IA square is, so determine the power of stable arc. They are asking the power. So for power we need to have voltage and as well as I. Okay, you can see we need to equate this two. So IT square, so you just square this one. IT square equal to minus 600, V minus of 60, IA is 20, V minus of 16 square, make it the square. So 20V minus of, why do you just make inside? I think so you are able to understand. So equate this, both of the things you need to equate, and you can see minus b, that's a minus root of b square minus of 4ac divided by 2a. Okay, so let me v voltage 1 and voltage 2 we need to calculate, and we need to apply this kind of voltage in any one of the equation. Okay, while you are applying, you can see voltage, you can see this one. So which one is the correct, you need to take that one, I need to multiply both of them and we will get this answer. Okay, that's it. I told about the melting thing efficiency, how each and everything is working. Yes, okay. So now we can just go to this question. Okay, now we can see this question. Okay, so you can see low carbon steel plate wire manual metal arc using, okay, open circuit voltage SCC, okay, arc length 4 and the travel speed v, and efficiency of the heat input. Okay, it means efficiency, it means efficiency of travel is 0.85. so efficiency of travel means, how we can just write, it means heat transfer divided by heat input. So heat input is voltage into I, this is the heat input. So okay, and voltage is given like this. Okay, calculate the heat input into, it means what is the heat input, it means we need to find voltage into I or total heat input. Okay, maybe this we can just calculate this according to, it means voltage is OCV 62 divided by 2 31. So SCC means I equal to SCC divided by 2. So like this. Heat input into the workpiece. Okay. So they are asking heat transfer to the workpiece. Okay, so it means 0.85 into of I, it means in this one, it means this one, we'll just get the heat transfer. It means heat transfer to the workpiece. Okay. So voltage is given, voltage equal to, since voltage is given, you can see voltage equal to this one. So 4 into 1.2, it's about 1.5, it's about 6. Okay, 6 to 20, voltage equal to 26. So calculate, okay, so 26 into, we need to calculate that's maximum. Okay, that 31. Okay. So voltage we have just calculated. So it means V divided by OCV plus I divided by SCC equal to 1. So based upon this, voltage is 26 divided by OCV is 62 plus I is, we don't know, I divided by SCC is 130 equal to 1. So calculate I will calculate 75.4824 mm per become. So power equal to P into, so 26 into 75, power is equal to 196.582 volt. Okay. Now we have to just multiply with 0.75, sorry 0. Efficiency. So they are just asking heat input to the workpiece. Okay, they are not asking the voltage drive. Okay, you can see 85% only goes, remaining 50% will go outside. So okay, so you can just see, go to the next question. So here, heat transfer to the arc welding of the plate using current. Okay, current we have given. Heat transfer, okay, heat transfer is 90%. So 0.01 is equal to heat transfer divided by heat input. Suppose to melt 1 millimeter cube, 10 joule is required. The cross section area is 30 mm square, and the weld speed is 5 mm per second. The melting efficiency equal to, it means heat of melt divided by heat of transfer. Okay. So material deposition rate is 30 mm cube into 5 mm per second is mm square is 150 mm cube per second. This is a metal deposition rate. Means area into velocity, metal deposition rate. It means you can see this much 150 millimeter cube of the thing is being melted. It means, I think so, it means this volume. So for 1 millimeter cube, how much thing we need? 10 joule. Then for this entire melting of this one, how, it means how much energy we need? 150 mm cube per seconds into 10 joule per mm cube. So mm cube, so equal to 1500 joules per second. So per second we need this much amount. It means this is the total heat required. Okay. Okay, then what is the heat input? Okay, the current, it means voltage and I is given. Because based upon this heat transfer 0.90 to 250 into 20, we will get the heat input. Okay. You can see about this one. So efficiency of melting efficiency equal to, it means total heat melted divided by heat input. Heat input is 0.90 into 2. Power is, what is the unit of power? Watt is joule per second. Okay, so this one is how much? This one 1500 joule per second. So make this equal. So we will get the answer. Okay, I think so you are getting the point. So you can just go for the next one. So 20, this one traveling speed, area joint. Okay, heat required to melt steel, okay, the same. So the entire thing is same. Okay, you can just calculate this one. So you can go for this question. So in this you can see 2, it means 2 mild steel butt joint. Okay, voltage is given 20 volt, current is okay, welding speed given, filler wire of mild steel having filler wire. Okay, this one is filler, welding is occurring. Okay, diameter is 3 millimeter. It means the diameter is having, directly it is cylinder. Filler wire feed rate is selected. It means filler wire feed rate is selected such that the final weld bead, it means this final weld bead consists of 60% volume of filler and 40% volume of plate. The heat required to melt them, it means mild steel. It means okay, it means the mild steel is filler mild steel. To melt this one, how much it required? 10 joule per millimeter cube. Heat transfer is 0.7, heat required to melt is 0.6. Heat transfer factor. Heat transfer factor, what is this? I think so, heat transfer factor is 0.7. Okay, melting say the feed rate. It means they are asking the velocity of filler equal to mm per second. What is the velocity? total velocity of the bead, total velocity is 0.60, velocity of it means volume of filler plus 0.40 volume of plate. Okay. Velocity of the feed means in millimeter per second. Okay. So it means heat transfer efficiency, heat input, heat transfer divided by heat input, and heat of melting is heat required to melt divided by heat transfer. Okay, then definitely heat transfer, heat required to melt will get. Okay. So heat transfer. Okay, heat transfer, we can just calculate the heat transfer is, so 20 volt into 150. So we can see heat transfer is it means 0.7 into 20 into 150 heat transfer we just got. Okay, put here and we will just get a heat required to melt. Yeah, but this one heat required to melt, this one. Okay, this one 40% of the volume. Okay. Heat required to melt, it means 0.7 into 20 into 150. So total heat transfer is 210 watt joules per second. Heat required to melt is 0.6 into 210 into 0.6. So heat required to melt is 120 joule per second. It means 120 watt. So okay, it means 40% of the, it means this one is being melted. Okay, it means joule per second. It means volume of it means metal melt we need this one. So heat required to melt for metal is, okay, so 126 watt is required for melting of, joules per second is required for melting of for 1 millimeter cube of metal. So here 40% is being that metal, so we don't know the total metal. Okay, because they haven't given any kind of area. So let us assume volume is 1000. No. Okay, let us control this. So metal deposition rate is area into welding speed. Okay. So the same thing, metal deposition rate for this one is for a plate. Next one, this one is for filler wire. So filler wire area of weld bit into feed rate. So area of the this one is pi by 4 d square into a feed rate. Okay. So metal deposition rate. So let us match the thing. So this one entirely is millimeter cube per second, and the heat required to melt the this one is into 10 joule per millimeter cube. Okay. And the next thing, 40%, it means 0.40 millimeter cube into this, especially this one 126. It means we don't know how much volume that is being need to be melted. We came to the correct conclusion, but 126 joule per second. So this thing is cancelled. And metal deposition rate, and definitely here one other millimeter cube need to become. Let us go. Instead of going with the filler, it means instead of going with the it means feed velocity for which one, for filler only we need, so 0.60. So we came to a good thing, but you can see here pi by 4 d square into feed rate is entire thing is millimeter cube per second equal to, here also the same thing should become, okay, millimeter cube per second, okay. This side also definitely the metal deposition rate is, this side metal deposition rate for filler metal, okay. So it's about 0.6 into this one 126, okay. How this joule per second, okay, that we can just see now. You can see, oh, there is another formula also, oh wow. Okay, wow, this is also one of the interesting formulas. So you can see heat required to melt is metal deposition rate into of heat melt, okay, heat required to melt. So heat, it means what is the metal deposition rate, so heat, it means HMS, how much, about this one, okay, HMS, you can see this one. So it means, I think so, you can see this one. So HMS how much, 126, 120 watt equal to heat required to melt is divided by 10 equal to metal deposition rate. So HMS how much, watt, this one joule per mm cube. So joule can say metal deposition rate in terms of joule per second. Okay, now this kind of in joule per second. Okay, now we can just find the, wow, such a good question. Okay, that's a good question. So I think so you can calculate the remaining thing CC. So calculate electric power P equal to voltage into I. So calculate heat transfer equal to, this one I think so, you know, heat transfer metal deposition rate equal to millimeter cube per second. So sometimes we can write the metal deposition rate in terms of joule per second also, or millimeter cube per second. So just we need to equate the equation, we can just calculate it in an equal way. And heat input, okay, heat input again joule per second, millimeter per second, you can see second cancel, and joule per mm, okay. And for 1 mm how much heat we need, okay, I think so you can be able to do this one. So I think so guys, that's it for this today's video, and okay. Maybe in the next class we will complete the entire welding chapter. Okay guys, then finish in the next video. Until then, take care, bye bye, have a good day.